First, a great thanks to Martin and his talk from Western Digital, and as you heard, they're very supportive of us. This is an interesting day for us. We're kind of coming out of a stealth mode here. We've kind of had this title placeholder for the talk, so we didn't announce prematurely exactly what we're going to say. But we've decided now is the right time to tell you a little bit about what these Esperanto people have been doing. You've probably seen them on a number of committees. So we're going to talk about high-performance RISC V today. This talk comes not necessarily in the perfect order here. There are actually three different presenters from Esperanto today. Chris Saleo is going to be talking about Boom tomorrow at 9:30. Chris has joined Esperanto, and so a lot of people saying, hey, what's going to happen to Boom? We wanted to use it. What's going on? It's okay. Esperanto is going to allow Chris to continue to manage and support the open source Boom repository. We expect that probably is going to move over to something called the Free Chips Project in the future. You'll hear more about that later. But what we're going to do is to take Boom, which has been absolutely spectacular piece of work done by one PhD graduate student, but we want to move that to even higher performance levels. So we'll talk a little bit more about that today and what we're going to do. But when you want to hear, I won't talk about a lot of the details of that particular core here. Wait for Chris's talk and he'll give you more details. Likewise, Roger Esposa is going to talk tomorrow about progress on the RISC V vector instruction extensions. He and Kirsty have been leading that proposal. It's looking really nice. I think it can be the best vector ISA out there. And what Esperanto is doing is we have been implementing a vector architecture here to understand the design trade-offs. And I think Kirsty said it was very good earlier when someone was talking about the hypervisor. It's good to implement first before you nail down a specification here. So we're using this implementation to gain feedback about what are the right things to put in the vector architecture. So Roger also will talk about the details of that. I'm not going to talk about that in my talk today so much. What I'm going to do today is to answer the question, what are all these Esperanto people doing? We've been in complete stealth mode until now. And although I'm going to talk about general directions, we're not doing a product announcement today. Again, we want to be part of the RISC V community here to have you kind of understand what we're up to so we can all work together here. So some of the things I'm talking about are works in progress and subject to change, and we want to be able to get your feedback here. So I want to start off by talking about our perception of RISC V a little bit. And when I saw Kirsty do one of his first RISC V talks at, I think it was at Stanford University, I went and went, God, it looks awfully simplified. Is this really going to work or not? And we had already started Esperanto. We were actually doing our own new instruction set for something else, for a customer that thought they wanted us to do something. But the more I studied it, the more impressed I got. We actually did a study where we compared ARM versus RISC V, and I expected to see RISC V take 20 or 30% more instructions, and we were kind of shocked. We measured every instruction and spec benchmark. There was only a 1% difference in instruction dynamic path length. So RISC V has done well. I see basically all the university research work now is on RISC V. Even companies like IBM are doing a lot of research work on RISC V. I'm very impressed with the work that was done with Chisel and some of the other CAD innovations. They provide a lot of benefits in rapid design, and we've seen that as we've been working with Chris Saleo on Boom. Rocket has just done amazing stuff out there. It's helped launch many projects and actually products with different companies. And we now have a variety of companies already offering RISC V designs and intellectual property out there. So RISC V, I think, is really doing well. It's starting to gather mind share, particularly in the embedded space. But I come from high performance design, and for example, I go to the supercomputing conferences and I ask people, hey, have you heard about RISC V? And they say, isn't that just kind of for university, for teaching students? They kind of view it still as a curiosity and a toy, only for the low end. And so we went out and talked to a lot of people to figure out, what was the perception and what was lacking still in RISC V. So why wouldn't you want to use RISC V? And we kept getting a common set of questions. They said, well, I'm using ARM today. Where's the RISC V alternative to a high-end ARM CPU? Yeah, come back to me when you've got that, right? And though I personally really adore Chisel and the productivity, it's not really what a lot of the experience base is out there in industry. So say, when can we get a high-end RISC-V with human-readable, synthesizable Verilog? We kept hearing that question. When will we see RISC-V with compelling performance in a leading-edge technology node? When are we going to see 7-nanometer RISC-V, right? We haven't seen that yet. And in experience I had at the former company I was at, we did a CPU that was twice as good in power per performance, and came back and somebody would say, oh, well, the CPU is only 5% of the die area, it's all graphics, right? So even if the CPU is better, does it really matter? When are we going to get graphics for RISC-V? You guys going to go out and license a graphics core from ARM to put on your RISC-V SoCs? That seems kind of dicey. And just generally, a lot of the processor interest these days is in things like machine learning. When are we going to see RISC-V processors really doing well at machine learning? When are we going to see something for HPC? So as we thought about the market and what we can do, really, we want to complement the other players there. So first, I want to say, kudos to people like Sci-Fi and Andes. They've already got stuff out there. And so, they've got kind of a piece of the pie there. We view these people as our partners. These are not our competitors. What we want to do is expand out of the whole the pie of microprocessors. We want to grow the part that RISC-V takes. So we wanted to find a piece that these other people were not playing in and take it out of you-know-who, right? So we thought about how could we best go off and do that. So we are a startup company, right? But we have everybody at our company has a passion to help RISC-V succeed. We're not doing this as a job. A lot of us really come from backgrounds in high-performance processor design and also low-power processor design. And so our view was the place we could make the most impact was in the high-performance area. So what we are designing, we are doing a high-performance RISC-V core that we will think will be at levels of performance comparable to the best IP core that you can get today. We're not just doing one core, we're actually doing at least two or three. But the other second main core we're doing is we're going to focus on doing high teraflop levels of computing. And our goal is to make RISC-V more compelling than those other high-end alternatives. So how are we going to do that? Well, to start with, we are and have been designing for the last 2 years in leading-edge 7-nanometer CMOS technology. Okay? We're going to design both the highest single-thread performance for RISC-V integer applications and also for the best teraflop per watt. Okay? We're going to use design methodologies that are comfortable for the customers that we want to use our parts and potentially license our IP. So that means although I like Chisel and other things, we've got a lot of demand for people who say, hey, I want to see this with a standard CAD flow from the major CAD vendors, Cadence, Synopsys, Mentor. I want to see this, and particularly, where's the design in Verilog, right? We get a lot of requests for this, and I think it's more because a lot of companies who are building big, complex SoCs, they already have a lot of their internal ecosystem and engineering talent already trained in Verilog, and there's a lot of commercial tools to help manage Verilog, do lint-like things out there. So we took that as a strong consideration. The other thing we're going to do is very strong physical design effort in what we're doing here. Again, it takes more personnel to go off and do this, but we think it's worth it because energy efficiency is so important in this high-performance area. It needs a very careful trade-off of architecture, circuits, and physical design. In part, what we're trying to do is to build a flagship for RISC-V. We want a product that's going to draw attention to great RISC-V performance. So we were faced with, okay, we're going to build an actual chip and sell it. What should we build for that first product to get the most attention? It's probably not too hard to guess here. But our mission is we're going to build the highest teraflop per watt machine learning computing system. And the benefit is it's going to be based on the RISC-V ISA. Okay? So we're going to build a couple different processors. Our high single-thread performance processor, we call it a Maxi. These are kind of internal code names for the moment. They may change later. But we kind of got used to internally on this notion of calling them the Maxions and Minions. So the goal of the Maxion is to allow RISC V to be positioned alongside the highest performance processors. And we want to enable companies like Western Digital has done to feel that they can make the transition top to bottom with RISC V, and they're not left at the mercy of having to go to another vendor because there's a hole at the high end. And let me tell you, having been in this processor business for a while, there's a lot of arm twisting, not to mention any company names, or other companies out there that if you don't pass the loyalty test, if you start to use something else, your pricing structure can change. And so people are afraid to make that transition if there's a missing hole at the high end. So we want to make sure there's not a gap there and people feel not only free that they can transition and not be losing performance, but we want to show them spectacular performance at the high end as well. So our performance goals are to have the best single-thread integer performance comparable to other IP cores that are out there. And in particular, these are cores going to be running multi-processor Linux system. It's to run the OS and to run the applications. Just a few specs on what we'll be doing. Of course, this will be a 64-bit processor. We want to use kind of the baseline. I think the proper way to say it's the RV64GC, I think is where we want to get a broad base of software apps out there to use this. And then, you know, other extensions will come in later, but I think this is the common baseline we want to use. For our Maxion, we're going to be starting from Boom version 2, okay? So you'll hear more about that tomorrow, but expect where we're going to take this. There's very substantial changes. Good work for one student, but when we put a large team of people on this, we can improve the performance substantially. It'll still be an out-of-order pipeline, multiple levels of cache, multi-processor support, and you know, it's not just work per clock, but it's also clock rate. This is going to be highly optimized in the physical design for 7-nanometer CMOS. We're going to use this in our product, but we're also, along the way, we can't design all possible products. We're going to make this and our other cores available as licensable cores. Why? It's not because we want to be an IP core business. That's really not our focus, but we want to help expand the RISC V ecosystem there. We can't design all possible chips. We want to help the rest of the community get their chips designed as well. Our second core, we call it an ET Minion. And a lot of people have used the name Minion. Again, this was kind of a code name, so I'm calling it ET Minion so you can distinguish it from your own minions out there. But the goal of the Minions is to do all the heavy floating point work. So these are designed to do a lot of flops per clock, but they're also specifically designed in a particular style for energy efficiency. Future computing is all about reducing the energy per operation here. So what we're building is, again, a full 64-bit RISC V ISA, but this little Minion is going to have its own integrated vector floating point unit. And we're going to do the full vector instruction set, but as we're looking at areas like machine learning, we've added some instruction extensions. So one that we think isn't quite defined yet by the vector unit is good support for tensors. So we're prototyping this, and when we feel we get it right, we'll talk more about that. But we found that helps us with our energy efficiency, and we couldn't resist. We've added a little bit of support for graphics operations, and I'll tell you more about that. We've built this core so it can talk easily to hardware accelerators. When you go off through an accelerator, you have to wait for the accelerator to finish, and so you're sitting there waiting. So we've added multiple hardware threads of execution to absorb that latency and do something else while you're waiting for the accelerator to come back with the answer. Again, we're going to use this in our product, but we're going to also make this core available as a licensable core, not just kind of synthesizable Verilog, but we're going to do aggressive design in 7-nanometer for some of the physical design support, things like register files, caches, other things where the physical design is very important. So now we're going to put these all together in a product. So what we're building is an AI supercomputer on a chip, right? The design is fairly scalable in the number of cores up and down. We want to be very scalable in performance and power. We're not just going for the maximum die size and maximum power. We have customers that are very interested in fairly low power levels as well. So we're going to be very scalable. In terms of technical features, we're going to throw a good handful of our Maxi cores, currently planning roughly 16. So think of this as a 16-core SMP system running Linux. So this is a bootable chip. It's not just working as a co-processor here. And then on top of that, in 7 nanometer, you can put a lot of stuff. We're going to put over 4,000 full 64-bit RISC-V cores, each with their own vector floating point unit. We're not saying exactly how wide that vector floating point unit is today, but you do your own guesses of math. How many flops per clock times how many cores times clock rate? This is a lot of teraflops on a chip. We're going to have a network on chip design that's going to allow all these processors to reside in the same address space. Again, how we deal with the interconnect and memory system is critically important here. We're going to have high bandwidth DRAM interfaces, and again, all this is designed into one chip, highly optimized for 7 nanometer technology. And this is also be our first machine learning product, but the processors are general purpose. So we're not just focusing on hardware, we're also a software company. We have a mixture of hardware and software. So when we say we're good for machine learning, we've got to actually see how well does it do. When we look at the machine learning world today, there's a lot of announcements, new companies wanting to do chips. They've all got some kind of proprietary special purpose instruction set. What are you going to do with that? I mean, the strength of RISC-V is we're going to get a lot of software there. So we believe a better approach is to base all of our processing on top of RISC-V. That lets us leverage the OS, compilers, everything you guys in the community are developing. And where necessary to be as good or better than the other guys, we can add some additional instructions if we need to. That's the flexibility of RISC-V. And we can add hardware accelerators if we have to. So our general approach is thousands of energy-efficient RISC-V cores, each with vector capability, a few instruction extensions like tensors. So let's see how this runs. So here's one of the most famous deep neural network programs. It's called ResNet 50. We have our software stack running, generating RISC-V instructions with the tensor extensions. This is running on a full Verilog RTL clock-for-clock level simulation on our ET Minions here. And what you can see in the bottom right here, these are all 4,000 processors. When they turn bright red, that means the processor is busy. And you can see out of the total peak performance here, we're actually able to sustain pretty good levels of performance here. So this is running inference on one batch of 8 images, the batch size of 8. Doing all 52 layers. There are actually 52 layers in ResNet 50. It's not ResNet 52. So we've been able to get very good insight into how machine learning will run on top of our core. Well, that's great, but we're not limited to just running AI-type programs. We have a general purpose set of processors underneath. What about graphics, right? And we think for the RISC-V community, how are we going to all build SoCs if we don't have a graphics solution? So we had a few people thinking about that as well. And one of the considerations was, well, we've got thousands of cores. High-end graphics has lots of shader processors. They're not that different than a RISC-V processor here. How well could we do? Well, if you want to run high-end video games, the first thing you need is a shader compiler, right? So we went out and we built one for RISC-V. And the code to distribute those shader programs across all 4,000 of our cores. And the results were pretty good, a little bit actually better than we had hoped. So again, we're not quoting performance here. This is just a little bit of an update. But for those of you who have been in computer graphics, you may recognize some of these games. Crysis is a fairly old game. Atom is a very new, a little bit tougher game to do. But to be able to fully render complex scenes like this from a shader compiler. It means your shader compiler is going to be pretty bug-free, right? And running on full Verilog RTL means we've got a pretty good understanding of what it takes to do graphics at this point. Okay? So the message I want to have for the community here is we don't need to abandon RISC-V to go off and build processors for machine learning or to even build a GPU. We don't need to abandon RISC-V, right? And so we think this trend of building proprietary instruction sets for machine learning is not one we have to follow here. In particular, the algorithms are changing so fast. I think there's more safety in sticking with a more general purpose platform. Then as the algorithms change, we can adopt a slightly different acceleration if we need to. But I think we need to challenge the claim that we need a completely new proprietary instruction set to do a brain CPU or something. I just don't buy it. I think we can do very well with RISC-V. So we think the better approach is to use RISC-V as a base instruction set and add some instruction extensions if necessary. That's the wonderful flexibility of RISC-V. So we can add things like the vector ISA if you need more floating point. Tensor instructions can help do specific algorithms for machine learning. And hardware acceleration can also be applied if you can't get there normally. But we have the freedom to innovate with the RISC-V ISA. And so we have time, and we're going to explore what are the right extensions to make for the high end. So generally, using RISC-V CPU plus domain-specific extensions allows us to grow and utilize the common software base for applications, and then we can access those extensions through library calls or other mechanisms, but again, preserve the code portability and grow the software base for RISC-V. So in general, what we're attempting to do, and what we hope the rest of you do, is let's make RISC-V processors potentially with domain-specific extensions, make them the better alternative to what anybody's doing on some other instruction set architecture. So let me summarize just a little bit what Esperanto is working on. We are building real hardware. We are building advanced computing systems for machine learning, for graphics, for anything else you can imagine running on thousands of general-purpose cores, all built on top of RISC-V. We expect to sell both chips and systems, and we think this can be the best machine learning chip in the world, okay? Not just the best on RISC-V, and a showcase for how good RISC-V can be. Since we're building cores, we're happy to license some of those cores. So we're going to license our ET Maxi, the highest single-thread performance. We'll license our ET Minion, the most energy-efficient RISC-V core for floating-point intensive apps. We'll license our graphics solution here. We have some clever approaches that can base a lot of this on RISC-V. And again, all this will be highly optimized for TSMC 7 nanometer, and then it should be fairly easy if you want to port it back into older generations of technology. We're also supporting free IP. We're going to continue to manage and support the open source Boom repository. And part of why we wanted to come out today and finally explain what we're up to is we have enough confidence in what we're doing to believe we can achieve all these goals, and we want to solicit the input and involvement of the RISC-V community in helping us achieve these goals, either just by working together, as we normally do, but we're also hiring. If you want to come join us, now's a good time. We're in a growth phase of the company, and we have a new website that just went live today, so feel free to check out some of the details there as well. Okay? Thanks very much.